Hello and welcome. We are from Avektive. Now we'd like to present you our approach of designing wind energy forecasting model with lead time of 18 hours. Here we go. In this task, we will play the role of an energy trader. The goal is to get a T plus 18-hour energy forecast for every hour. Using our energy forecasting model and the given trading algorithm, we will maximize profits for our client, which is wind energy producers. We will build the forecast model based on time series datasets using deep learning neural network, specifically the difference network architecture. The methodology as is follows. Firstly, we examine the data and its statistics. Secondly, we normalize the data and set our baseline risk. Thirdly, after we get the baseline, we fit the training and test set on risk function. Next, we improve the model performance and decide which model that produces the largest profit. And finally, we check the best model for reproducibility. The first dataset contains wind energy production for Ile-de-France region surrounding Paris that have been averaged and standardized to a time base of 1 hour. The data is provided from January 2017 to date. From the graph, we can see the data is not that regular, but we can still see some trends. For example, the spikes of energy are most common in the winter and in the transition between seasons. The largest energy produced occurred in the winter 2019-2020, which is up to 89,000 kilowatt per hour. The second data comes with two different wind forecast models, A and B, for 8 location wind farms in the Ile-de-France region, where each has two variables, wind speed and wind direction as a bearing. The forecasts are updated daily every 6 hours and have been interpolated to the time base of 1 hour. The wind speed graph has a similar trend to the energy one, indicating that this forecast data can be quite useful to our model as input features. Compared to the wind speed forecast, the wind direction pattern is tough to decipher, but we will see that even for such data can still bring benefit to our forecast model. Using mean and standard deviation, we normalize the data with this formula. You can see the change of data before and after being normalized. Notice that we only normalize the energy and wind speed data. The wind direction values will have special treatment later. We can extract the persistent loss value by adding persistence loss functions. Here, the persistent loss is our baseline to beat. We can see that the persistent loss with MSE and MAE are different. We will figure out what loss formula worked best to our model. Now we start with the experiment. Using difference network architecture, it helps us achieve better learning to beat this baseline. We fit the training and test set on risk function by tuning several hyperparameters as shown. In the first experiment, we used 76 input features in total with input scaling subnetwork and 4 hidden layers with various dropout prop and NN size and Adam optimizer. We use window consisting of 60 hours of past energy produced, and then we turn the window into diff, momentum, force inputs with a lead time of 18 hours. We also added an average of 60 hours of past wind speed forecasted and the wind speed forecast at T plus 18 hours from each model. Here is the test loss and predictions for experiment 1. We can see that we have beaten the persistence and achieved zero lag, but there is still a high gap between training and test loss. We can consider using regularization and adding more features. With the same model as before, we add the L2 regularization into our model. We take the wind direction forecast and feed it into trigonometric function to normalize it as the new input features. Now we have 84 input features in total. For the test loss and predictions in experiment 2, we noticed that we have produced a better test loss while maintaining zero lag, also increased the peak value of lag graph. We can still improve the performance by adding more input features or layers to the model. By setting the hyperparameters fixed, we include new statistic features as the new additional inputs. These are the mean and SD of T-60 hours of past energy produced and the SD of T-60 hours of past wind speed of model A and B. In the end, we have 88 input features in total. We achieved the best test loss using this last model while having no lag. We have better scatter plots of actual versus training test predictions. Although we fit well on the training set, obtaining a better scatter plot of actual versus test prediction is still a challenge. Previously, the final model above has been done 40 repeats of training where each takes a maximum of 10,000 iterations. Note that we use MAE for the loss function as it gives a higher profit to the clients, resulting approximately 14.5 million euros. So in summary, the difference networks are quite effective in building a forecasting model. In historical data, the diff window combined with momentum, force, and statistical features can help the model perform better prediction. Bigger and deeper networks support the model memorize well, but be careful of overfitting. Dropout layer and L2 regularization help the network handle overfitting problems, hence improve the performance. And finally, we use MAE because it works best for our model. That is all from Team Avektive. Thank you.